All right, let's get started. Review one today, and we'll be talking about my plan today is actually to go over the review sheet that the professor has put up, along with your last exam, actually. So let's do those two things. Start by sharing my screen. Hey, which of these are you? Yeah. Okay. There we go. So let's start with this. Let's go over this whole document and then come back and review your last exam. Okay, let me download this real quick. Oh, another important thing that I should let you know is that Professor Kowak offered me to write the final exam with him. Um, and so I will be creating a short list of questions that I think are reasonable and uh, sending it to him for his consideration. So the final will have some influence from my side. If you want to be successful in the final, go through the recitation recordings, go through the questions that we did, pay attention to this review and the next one. And from my side, you should be good. All right. Can you all hear me okay?
Are we going to go over the practice questions he gave?
Yep.
Okay.
First thing I'm doing. Yep. The final practice questions you're saying, right?
Yes.
Yeah. Okay. Check. Awesome. Great. Let's get started. Um, cool. First question, and I'm not gonna spend as much time as I would do in class, right? Where I would go over each in the process of going over the question, I would also use that as an opportunity to go over the theory. Now that you're all prepped with the theory, I'll dive straight in and sort of give you a taste of how someone who's like gone through and reviewed all of my recordings and who has all the theory background to begin with would approach and start solving these problems straight away. Okay, first question. What is the molarity of an 18% by weight calcium chloride aqueous solution? And the density is given to be 1.169 kilograms per liter. First thing I see that is that it's a percentage. And so I start by taking 100 and it's a percentage by mass. So I'm going to start by taking 100 grams of the solution, which will now be 18 grams of calcium chloride, and the rest is water because it's an aqueous solution. 100 minus 18, 100 minus 20 is 80. So that's going to be 82 grams of H2O. And now what we want is molarity. So let me start by writing down the molarity formula. It's the number of moles of solute, in this case, calcium chloride, divided by volume of solution. Volume of solution. Okay, the first thing deals with calcium chloride. Calcium chloride is 18 grams. Let's convert that into moles by dividing by molar mass. Calcium, I believe, is 40 in the periodic table, 40 grams mass. Chlorine is 35.5. Could be wrong. But then there's two of these guys. So that's 71. 40 plus 71 is are you allowed calculators on your exam?
Yes.
Okay, I'm just gonna do this in a calculator then. No, I don't need to do this in a calculator. Let's see. 100 plus 71, 40 plus 71. That's 101, 111, I believe. Try not to put anything in the chat because for some reason and it's not your problem, it's mine. I need to always stop sharing my screen before I can see the chat for some reason. So just feel free to interrupt and tell me what you want to say. And if you have the answer for a specific thing that I'm doing, chime in. That's good. So this comes out to 0.162 moles. And then lastly, we have 82 grams of water, but that is not useful information because we want volume of solution. Solution is not just water, solution is everything. So we have 100 grams of solution. This is the density of, they should have specified, of solution. Cool. What's the density equation? Density is mass over volume. And so volume is mass over density, rearrange algebraically. So volume is mass of the solution, 100, divided by density of the solution, 1.169, gives you volume of the solution, 85.5. But now you have to be careful because the density is given in kilograms per liter. And so I need to convert this into kilograms, 0.1 kilograms. So the mass in kilograms is 0.1, the density, that's why it helps to write out the units explicitly to see if they cancel. Kilograms per liter, and so the kilograms cancel as they should. And you get 0.1 divided by 1.169. Liters, which is 0.0855 liters. I'm being very sloppy with sig figs. You know how to do that. All right, so let's put everything together. 0.162 moles of calcium chloride divided by 0.0855 liters of overall solution. And that is the answer. Remember, units of molarity is moles per liter or big M, molar. Moving along, question 2, what is the boiling point of again, 18%. So I'm going to take 100 grams of calcium chloride solution.
I have a question. Where did you get for a number of moles CaCl2? Where did you get 0.162 from?
By dividing it by the molar mass of CaCl2, which was about 111.
Wait, what did you divide by the molar mass?
111. 18 divided by 111.
Oh, okay. Thank you.
I think 111 is the correct molar mass of calcium chloride. If not, just look at a periodic table and calculate it yourself. Okay, good. Thanks for the question. Question 2. So I'll be going quickly. If you want me to slow down, you'll have to tell me. The one reason that I'm going quickly is because I want to cover as much material as I can in these 2 reviews. And if I'm going a little too fast, you can always come back and watch the recording. But if you have a question, just like Iman did, interrupt me and ask me. 100 grams of solution goes into 18 grams of calcium chloride, and the rest, 82 grams, should be water. Density of the solution is given, and my KB is given. This is a boiling point question. Colligative properties. Delta TB equals I times a constant times M, molality. Delta, remember, always stands for solution minus pure. So we're going to expand that into boiling point of the solution minus boiling point of pure water equals I times KB times M. We want the boiling point of the solution. So solve for boiling point of the solution equals boiling point pure of the water plus I times KB times M. What is the boiling point of pure water? 100 in degrees Celsius. I is the number of pieces your solute breaks up into. Calcium chloride breaks up into calcium, 2 plus, and 2 Cl minuses for a total of 3 particles. So I is 3, KB is 0.512. Little m is molality, and that is something we need to calculate on the side. Let's do that here. Recall, molality is number of moles of solute divided by kilograms of solvent, and so in this case, water.
Where did you get the 100 from again?
Boiling point of pure water.
Okay.
Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Okay, so it's moles of calcium chloride divided by kilograms of water. Moles of calcium chloride, I see it's 18 grams. We did it for 18 grams last time, 0.162. 0.162 moles divided by kilograms of water. I've got 82 grams of water. Convert that into kilograms, 0.082, dividing by 1,000. And that gives you 1.975 moles per kilograms, or little m, molal. Cool, so that number goes here, 1.975, and you should get the final answer to be 3 times 0.512 times 1.975 plus 100, about 130 degrees Celsius. So the strategy was I looked at the keyword boiling point, immediately took me to the only equation that I know for my boiling point, which is colligative property equation. And the KB is also a hint. KB only appears in that equation. And it's also a percentage question. So you start by assuming 100 and break it down and take it from there. Cool. Moving along. Question 3. Label the following on a phase diagram of carbon monoxide, solid, liquid, gas, critical point, triple point. Cool. This is how I remember. In the region where temperature can be increased as much as possible, without ever hitting a boundary, well, that has got to be gas, because if you heat something up indefinitely, it will become a gas eventually. So this is the gas area. If you can increase the pressure on a substance indefinitely, that is this region, then you will eventually turn it into solid because you're like compressing it. So this must be solid. And so by exclusion, this is liquid. You'll see that usually you have 3 regions, but here you have 4 regions. And that is because carbon monoxide exists in 2 possible solid states. How do we figure that out? Let's think about it. Look at what's happening here. You have 1, 2, 3 phases coming together. That's a triple connection. That's a triple point. So, okay, this is triple point. We're answering these questions without even knowing what is here. Just because this point lies at the intersection of 3 different colors, it's got to be the triple point.
Can't the lower point also do that because it's intersecting 3 different colors?
All right, that is also the triple point. They're both triple points now. No, they're not. And here's why. Oh, man. The top one is a triple point. The bottom one is not a triple point. It is, okay. Yikes. They should have told you.
Isn't the top part the critical point?
It would depend. If this is liquid, right? Then this point lies at the intersection of liquids Oh, interesting. Oh, I see. You're right. You're right. You're right. So annoying. This is liquid. This is something where you can increase the temperature indefinitely. So that can't be liquid, right? Here, there's no limit to temperature. So this can't be liquid. That's liquid. Okay, great. So this is now this marks the end of the region between liquid and gas. So this is critical point. Yep, you're right. Past the critical point, everything is, so this part, this shaded part is supercritical fluid. Supercritical fluid. Now down here, now that lies at the intersection of solid, liquid, and gas. So that is indeed the triple point. Okay. Does that make sense to everybody? This is a tricky question.
Yeah.
It is tricky because usually in our phase diagram, we don't mark the supercritical fluid as a separate color. But here they do. So that is the tricky part, at least for me. Awesome. Does carbon monoxide sublime at 1 bar pressure? 1 bar pressure. Okay. So I've given my pressure, so I just need to figure out where that lies on this pressure axis. But if you see, the pressure here is given in MPa, megapascals, and my pressure here is given in bar. So let's do a quick unit conversion from bar to MPa. We don't want bar. We want, I think we know how to go from bar to pascals, where 1 bar is 10 to the 5 pascals. And then we can use that as an intermediate unit to go from pascals to megapascals. 1 megapascal is, mega is 10 to the 6. Cool. So the bars cancel, the pascals cancel, and the megapascals remain. So that's 10 to the 5 divided by 10 to the 6, which is 10 to the negative 1 megapascals. 10 to the negative 1 right here. So we're not given any specific temperature. So the question is, at any temperature, can you sublime at 10 to the negative 1 megapascals of pressure? Let's see. At the first crossing of the boundaries, we're going from solid to liquid. So this is not sublimation. At the second crossing of a boundary, we're going from liquid to gas. That's evaporation or vaporization. That's not sublimation either. And after that, we're not crossing any boundaries anymore. So no, at 10 to the negative 1, CO does not sublime. What about if the question had said, something like 10 to the negative 2 megapascals down here? Look over there at the first boundary, we're going from solid to gas. So yes, at 10 to the negative 2 megapascals of pressure, CO does sublime at some temperature. And if they also ask you what that temperature is, just look at the x-axis. That's about 20, 40, 60, 80, 100. That's about 60, 65 Kelvin of temperature. Okay, that's how you read these phase diagrams. Moving along. Question 4, calculate the pH of a 0.2 molar aqueous hydrochloride acid solution. pH, an acid. This is acid-base equilibrium. First thing that I think of, hydrochloric acid. What kind of an acid is it? Strong acid. Anything else given in the question? Nope. So this is strong acid in isolation. Okay, strong acid will do its thing. It will completely break up into H plus and Cl minus. Since I'm getting started with 0.2 molars, all of that is going to be converted into 0.2 molars of H plus and 0.2 molars of Cl minus. I'm going to calculate pH. pH is the negative log of either H plus or H3O plus, same thing. And so that's just the negative log of concentration, i.e. molarity of H plus, which is 0.2. Done.
So there's no need to do an ice table here.
Nope. Recall, strong acids, strong bases. The strategy is all of it dissociates. Weak acid, weak base. Ice table. Salts. Ice tables. Buffers. Depends. What you do with buffers is so buffer slash titration. Oh, actually, never mind. Buffers are Henderson-Hasselbalch. Henderson-Hasselbalch equation. Titration depends. And it depends in the following way. You look at what survives at equilibrium. In titration, it depends, but the first step is always an ice table. Use a fake ice table. Fake as in there are no X's in the ice table. You know what the change is. And depending on what survives at equilibrium, you can have one of three cases: the strong plus the weak. Strong dominates. No ice table. Sorry, strong and salt. Or you can have weak and salt. Then it's buffer. No ice table, Henderson-Hasselbalch. Last case is only salt survives at equilibrium. I'm omitting water. Water survives in all of these cases, but that's not the important part. Salt, another ice table. This is the only titration question where you use a second ice table in titration. Okay. Question 5. Given that the delta H vaporization for a solvent is 43 kilojoules per mole and the normal boiling point at 1 bar is 122 degrees Celsius, what is the vapor pressure in units of bar at 55 degrees Celsius? Vapor pressure and temperature. That should remind you of, what is it? P ln.
Is it the Clausius Clapeyron equation?
Yes, excellent. Thank you. Clausius Clapeyron, I think, equation. And can you tell me what the equation is? I forgot.
I think it's ln of PO equals RT over enthalpy vaporization plus C.
ln of P equals
RT and over enthalpy vaporization plus C or K.
plus C.
Yeah, I think that should be K then.
Yeah. And the other version of this Clausius Clapeyron, the often used one is ln P2 over P1 equals
HVAP over R times 1 over T2 minus 1 over T1.
Yeah.
Which one's better to use though?
Oh, you don't want to use this one.
Oh, okay.
Yeah. So you said ln P2 over P1 is what?
Yeah, equals enthalpy vaporization over R times 1 over T2 minus 1 over T1. Yeah.
Great. Thank you. Yeah, that's the equation we'll be using. So P2, P1, T2, T1, right? That's the order. Okay. In the original Classics clip run, I think RT goes on the bottom and delta H goes on the top. And then these two equations are consistent. Anyway, let's focus on this guy. This thing down here. We're given, okay, so ln P2, I don't know. P1 is 1 bar. P2, I want it also in bars, so let's just keep it. Let's just keep both of our things in
Is there
bars.
not a negative next to the A?
Yeah,
Is there not a negative next to the? Oh, I just see it. Never mind.
I just put it there because you said it. Let me
Okay.
double check. Class. Right.
Because I think if you don't put the negative, then you have to switch the T's.
Yeah. Okay. Yeah, you're right. You're right. There should be a negative. If you want to keep the same order, P2 over P1, T2 minus T1, and then you want to keep introduce this negative. Yeah, you're right. Okay. All right, let's plug everything in. Delta H is 43 kilojoules per mole. I don't like kilos. 43 times 10 to the 3. 40 negative 43 times 10 to the 3 over R. This is enthalpy of vaporization that deals with energy, right? It's the energy of vaporization. So we want to use 8.314. And then 1 over T2 minus 1 over T1. 1 over T2. So the temperature should always mean Kelvin unless they're being subtracted. This is reciprocal subtraction. Originally, it was at 122. So let's add 273.15 to both of these temps.
Yeah. Okay. Apparently there's a review part 2 Saturday, so that's good.
Yes, indeed. This is 395.15 and 55, 273.15. That's 328.15. This is 122 was the beginning, and this is the end. Okay. So 328.15 minus 1 over 395.15. Can someone who actually has a calculator do this for me? Because I don't. And in the meantime, I'll just call it that. P2 over 1 is just P2. Tell me what is the last step? Well, I can't see anything you put in the chat. Sorry.
Sorry, what worksheet are we working on?
I am working on the final review sheet that he posted.
Okay, thank you.
Mhm. Okay, so if ln P2 is some number, how do you isolate P2? What do you do to both sides?
Exponentiate.
Mhm.
Would it have been wrong to use Raoult's law?
Say that again.
Would it have been wrong to use Raoult's law? Raoult's? If I'm saying it right.
I'm sorry. I'm not able to hear what you said.
Would it have been wrong to use Raoult's law?
Raoult's law.
Yeah.
Yes, you can't use Raoult's law first because Raoult's law doesn't have enthalpy in it, right?
Oh,
Raoult's
okay.
law. Yep, Raoult's law doesn't have enthalpy in it. And it also doesn't have temperature in it. No temperature, no enthalpy, wrong equation. Conceptually, Raoult law is not for when temperature changes. Raoult's law holds when temperature is the same, and you have a pure solvent and you change it by adding some solute to it. Raoult's law tells you how the pressure changes on addition of solute. Here, we're not adding any solute at all. It's just solvent. All right, moving along. Question 6. Ooh, yikes. How many questions are there in total? Yeah, we'll get through all of these today. And then next review, maybe I'll come up with some difficult questions and we'll do some advanced review. Okay, chemical kinetics. We want to determine the rate law. The rate law is given by rate equals rate constant K times each of the reactants. So our reactants here are H2SeO3 to the power of M, I minus to the power of N, and H plus to the power of M and O. That's not a 0, that's an O. We'll have to remember that. Okay. The initial reaction rate was measured for various initial concentrations of reactants at 0 degrees Celsius. Cool, determine the rate law. Okay. So we're just gonna plug in all of this information into rate law one at a time, and we'll have a bunch of rate law equations. We have 3 things here. So we want to go ahead and choose 2 trials where 2 out of 3 things have the same concentration. Let's see. Let's start by keeping H2SeO3 and H plus the same. So if this is 1, and these are the potential candidates, but this is 2, and 2 happens here. Yep, this one. And the first one. Right, so we have fixed the concentration of H2SeO3 and H plus. Cool, let's write down let's plug in row 1 and row 6 into our rate law. The rate is given in the first trial to be 1.66 times 10 to the negative 7 equals K. Concentration of H2SeO3 is 10 to the negative 4. I'm gonna ignore the 1 to the power of M. I minus is 2 times 10 to the negative 2 to the N, and H plus is 2 times 10 to the negative 2 to the O. For trial 6, rate is 6.64 times 10 to the negative 7 equals K. First thing is 10 to the negative 4 again by design. I minus is 4 times 10 to the negative 2 to the power of N. And the last one, H plus, 2 times 10 to the negative 2 to the power of O. And you just go ahead and divide both of these. K, 10 to the 7 cancels, K's cancel, 10 to the negative 4 to the power of M cancel, and this cancels. Excellent, we're left with one equation. And so let's combine these 2 into the same power, take out the power. 10 to the negative 2's cancel, 2 and 4 cancels as 1 and 2. 1.66 divided by 6.64 is 0.25 equals 1/2 to the nth power. What is 0.25 as a fraction? 1/4. So what is n? What must n be? What power of a half gives you a quarter? That's okay. So if you can't guess it, then we do the log method, right? We have 0.25, 1/2 is 0.5 to the nth power. What brings down the power? ln. So take ln of both sides equals n times ln of 0.5, and then divide both sides by ln of 0.5, and you will know what your power should have been. If you do this, you'll see that n comes out to 2. So this is involving trial 1 and trial 6. And that gave us n. Cool. Let's now go ahead and fix 2 other things. Let's do these 2. And so for I minus, I want the same thing. So it seems like 1 and 5 will work this time. See, these 2 are the same, and these 2 are also the same. So repeat the same process with 1 and 5. That will give you the power of h plus, which is O. And then lastly, you want to fix these 2. So basically all possible combinations. Okay, 2 and 2. Where do they repeat again? Right here, 2 and 2. So you're going to do 1 and 3. And so 1 and 3 gives you m. Okay. So you do this 2 more times. And then how do you solve for k? Pick any one equation. Let's say the first one. 1.66 times 10 to the negative 7 equals k 10 to the negative 4 to the power of m 2 times 10 to the negative 2 to the power of n 2 times 10 to the negative 2 to the power of o. Once you've solved for m, n, and o, plug them in here and solve for k. And you're done. Okay. Any questions? Give me 1 second. Right, I'm back. It is cold. Moving along, question 7. What is the pH of a solution made from 25.5 milliliters of acetic acid and 1.32 milliliters of 1.2 molar NaOH? Okay, acetic acid, that is a weak acid. NaOH, that's a strong base. Huh. So we're doing weak acid and a strong base. That is titration. Okay, first ice table, fake. Let's make that happen. Acetic acid. If you can't remember the formula for acetic acid, not to worry. You can always go with this dummy representation of an acid. Acid looks like this. It has something, it has an H with some other stuff, A. And base, if you didn't, if you forgot what a certain base looks like, just write it as BOH. But you also have to remember, this is for monoprotic and monobasic acid. So if only one H plus or one OH minus can be given off, this is the general formula. If it's a diprotic acid, then it's got to be H2A and BOH2. If it's tri, so on. Acetic acid, the least you should remember about it is that it's a monoprotic acid. So I can just write HA. Cool. HA plus NaOH. They have given us the formula. Awesome. This will form, you don't even need the full thing, just say that it's a salt and maybe water. Okay, now let's make our fake ice table. And remember, in titration, it is better to work with millimoles rather than molarities. So let's do that. So this is in millimoles. Make sure you make a note of that. 25.5 times 1.4 for the acid. Let's see what that comes out to. 35.7. And for the NaOH, it's 32 times 1.2, 38.4. Water, don't care, because it is liquid. Okay, now subtract away the thing that is present in the lower amount, the limiting reactant. So minus 35.7 minus 35.7 plus 35.7. This gives you a 0. The next one gives you 38.4 minus 35.7, 2.7. And 35.7. So what survives at the end is the strong base and salt. Recall, if a strong base survives, it dominates. And so we need only find the pH corresponding to the strong stuff. But this is in millimole, so let's quickly calculate the molarity, because that is what goes into the negative log. Molarity of NaOH is, it's millimoles, 2.7, divided by total milliliters. We combined a solution that has 25.5 milliliters and 32 milliliters for a total of 57.5 milliliters. The millis cancel, and so you get moles over liters. That is concentration, that is molarity. And that is 0.047. Big M. Okay. Strong bases, what they do is they completely break down into OH minus and the remaining stuff. So that's 0.047 molarity that has disappeared to make 0.047 of Na plus and 0.047 of OH minus. And so I have OH minus information now. What can I calculate, pH or POH?
POH.
POH, excellent. So POH is the negative log of the OH minus concentration, which is this. Say it comes out to a certain number, and then pH is just 14 minus POH, that number. Okay.
You said it's 14 minus OH?
14 minus POH.
POH.
Yeah. Next question. Write a balanced nuclear equation for the following reaction. Alpha emission by actinium-227. Actinium AC, or you can look it up in the periodic table. I think it is AC. 227, that number goes on the top. Actinium, if you look at the periodic table, has an atomic number of actinium of 89. Alpha, it decays by alpha emission, so it makes a mystery daughter nucleus. An alpha particle, remember, is helium 2,4. And so following top number should add up and the bottom number should add up. The bottom number here should be 87 and the top number should be 227 minus 4, 223. Element 87 is francium. Oh my God. My father-in-law's name is Francis. I'm gonna message him today and tell him that there's an element named after him. Can't believe I didn't do that yet. Okay. Beta emission by phosphorus 30. Phosphorus P, 30 goes on top. What is phosphorus? 15. Creates a mystery daughter molecule and a beta particle. Beta is, remember, -1. Nope. No mass. It's an electron. Very little mass. Almost zero. Charge is -1. So the bottom number here should be something -1, which should give 15. So that would be 16. 16 minus 1 is 15. And the top number remains as 30. Okay. What's element 16? Sulfur. Great. Go back to our nuclear chemistry recordings where I went over much harder questions. Simultaneous alpha and beta emissions, or simultaneous alpha absorption and beta emissions. More than one alpha emission, right? 2 alpha particles emitted. So this is a very basic question. We did much harder ones. The aqueous solubility product of calcium sulfate is that. What is the solubility of calcium sulfate in pure water in molarity? Okay. I'm given KSP, so there's got to be an ice table somewhere. This is solubility, so let's see what calcium sulfate breaks down into. Calcium 2 plus and SO4 2 minus. This is solid, this is aqueous and aqueous. ICE. Let me move this whole thing away from here so that it's not in the way. Okay. All right. Solid. We don't care about this or this or this. Ca2 plus, initially nothing given, so 0, 0. And then if this is minus x, this would be plus x and plus x. And so at equilibrium, it's x and x. X here represents the molarity of calcium sulfate that got dissolved, the molarity of it. That's all they want. They want the solubility in molarity. Okay, so they just want X. KSP for this reaction is 4.93 times 10 to the negative 5. Equilibrium expression goes products on top with coefficients becoming powers. They're all one, so it's x times x to the power of 1 times x to the power of 1, which is x to the power of 2. Nothing on the reactant side because it's all solid, equals 4.93 times 10 to the negative 5. And so x is the square root of that. And that is the answer. Next question is related. The aqueous solubility product of calcium phosphate. Let's write down the equation for calcium phosphate. Okay, suppose you don't know what, so this is the tricky part here. You're supposed to read this and figure out what the chemical formula of calcium phosphate is. This goes back to one of the initial chapters where we did this. Remember, calcium and phosphate, that's what we're looking for here. Calcium is group 2, so its valency is 2. Phosphate is a polyatomic ion carrying charge of -3. So its valency is 3, just the magnitude. Crisscross, that gives you Ca3, PO4 twice. That is the chemical formula. So this was one of the tricky parts of this question. So this thing breaks up into 3 calcium 2 plus ions and 2 phosphate ions. Solid, aqueous, and aqueous. KSP is 2 times 10 to the negative 29. Don't care. Ice table. Calcium. Any initial amount of calcium? Yes, 0.25. Any initial amount of phosphate given? Nope. So if that was negative x, this would be plus x and plus x. So you have x and, sorry, 0.25 plus x and x. Set up the equilibrium expression. Products go on top, 0.25 plus x has a coefficient of 3, so to the power of 3. X to the power of 2, nothing on the bottom, equals 2 times 10 to the negative 29. This is a degree 5 equation. Can't do it exactly, can't do it analytically, so we need to use some kind of an approximation method. Our KSP is very tiny, so we can use small x approximation. That goes away. So you get 0.25 to the power of 3 times x squared equals 2 times 10 to the negative 29. X squared equals 2 times 10 to the negative 29 over 0.25 to the power of 3. And x is the square root.
So for this answer and then the question before, like, are we allowed to leave it in this format or do we like simplify it more?
I think you want to simplify it. You want to put that in a calculator and give them the final answer.
Okay, all right. Thank you.
Yeah. And correct number of sig figs.
I'm sorry, I have a quick question.
Yeah.
Why wouldn't it be plus 3x and then plus 2x for the
Oh,
coefficient?
you're right. I'm sorry.
Oh, okay.
I made a mistake.
Thank you.
Excellent. Right, so there should be plus 3x because of the coefficient and plus 2x. Very nice. 0.25 plus 3x and 2x. Excellent. Very happy you caught that. So this is 2x to the power of 2. Okay. And so when you take away the 3x, it just becomes 0.25, but the second guy, it's what makes a change. 2x to the power of 2. And so when you divide both sides by 0.25 to the power of 3 and take the square root, what you end up with is 2x. And lastly, to solve for x, you need to do 1/2 of that square root answer. Yeah, so that is the molar solubility. A variation on this question is for them to ask you the gram solubility. This is moles per liter. Let's say that this came out to something. Gram solubility is grams per liter. So you don't want moles, you want grams. The liter is fine. And so you would put in, you multiply this by the molar mass of the thing that is being dissolved. That molar mass would go in here. And that gives you the gram solubility. Cool.
Wait, how do you know they're asking for the gram solubility?
No, here they're only asking you for the molar solubility. So
Oh, okay.
solubility and molarity. I'm saying this is variation. Let me put that in a different color. If the question had asked for gram solubility, this is what you would do. So this is gram, whoops. Gram solubility variation. You know what I'll do next review session? I'll take these review questions that he gave you and all the review questions that he's given for the previous exams, and I will come up with, I'll go over them and I'll give you a lot of variations on the same questions, right? Because chances are he's gonna take some of his exam questions from the review sheets. And so why not go over all possible variations of those questions? So if he modifies them, you'll see it in review, right? So, okay, that is my strategy for review 2, go over variations. Question 11, we have a total of, Jesus, this is a lot of questions. That's okay. Question 11, we've got time. What is the rate constant for a first order chemical reaction, first order in A, if the half-life is 145 seconds for the following reaction? Don't care about the reaction. All I care about is that it's first order, and I have this nice formula for K. K is ln2 over half-life. So it's just ln2 over half-life, which is 145 seconds. That's it. That's the answer. And the reaction was there to throw you off. Moving along, question 12, titration of a monoprotic weak acid with a strong base NaOH. Part A, what is the pH of a solution of the weak acid with an initial concentration? So weak acid alone. Give me 1 second. Okay. So the first question is about calculating the pH of the weak acid alone. Weak acid, remember, we need ice table. Weak acid unknown, it's just HA. So HA will break up into H plus and A minus. All of these are aqueous. So all of these are important. This is a true ice table. We start with 0.5 molarities here. Nothing here, nothing here. Minus X plus X plus X. 0.45 minus x, x and x. Set up the equilibrium expression, products on top, x times x, 0.45 minus x. And this thing has a Ka of 3.2 times 10 to the negative 4. Small enough? Don't know. Can we use small x approximation? It's not too bad. It's a quadratic.
Why is the top x minus x?
Oh,
Shouldn't
it's
it
x
be
times
x?
x.
Okay.
It is, yeah. Let me convert that into x squared. Or just x times x. That's fine. Okay, so small enough, I don't know. Let us pretend like it is small enough, and we'll do the 5% check at the end. So that goes away. And so you've got x squared over 0.45 equals this mess, or x squared equals 0.45 times 3.2 times 10 to the negative 4. Get rid of x, you get that. Can someone calculate this in a calculator for me, please? I think for this, I can use my iPhone calculator. Let's see.
I got 0.012.
0.012, thank you. So let's now perform the 5% test to see if we got away with this small x approximation. You take your x, which was 0.012, and you divide it by any of the initial numbers. In fact, take the smallest initial number, except 0. That leaves us with 0.45 times 100. 0.012 divided by 0.45 times 100 is 2.6%, which is certainly less than 5%, so this checks out. Whew. The small approximation is valid. Once you have your x, that gives you the concentration of H+. Last thing to do is to take the negative log to get the pH. And you're done. Next up, what volume of NaOH with a concentration of 2 molar is necessary to neutralize the weak acid? If you initially have 50, okay. For the weak acid, we have 50 milliliters and 0.45 molars. And we want to neutralize it with NaOH, which is 2 molars and a known volume. If you want to neutralize the weak acid and the weak base, then they should be present in stoichiometric number of moles. Since they're both monoprotic, the weak acid is monoprotic and the weak base is monobasic, you need 1-to-1 ratio, which means you need the same number of moles, or millimoles for that matter. So 50 times 0.45 should give you the same as the unknown milliliters times 2. And so V should be, all I'm doing is equating the millimoles of the acid and the base, because that should be the same for equivalence. So that's 11.25 milliliters. Cool. Part C, what is the pH at the equivalence point if you initially have 50 milliliters of weak acid with a concentration of 0.45 molarities? Yep. You need to use the answer from part B. Okay. So weak acid is HA, and then we have NaOH, gives some salt plus water, ICE. This is the fake one. And we're going to do in millimoles. So what was the millimoles of the weak acid? It was 50 times 0.45, 22.5. You don't need to multiply for NaOH because it is equivalence point. So this has got to be 22.5 also. And so all 22.5 gets used up as it should in an equivalence titration. So you've got 0, 0, and 22.5. All that survives at the end is the salt. Now remember, the salt has both the conjugates of the acid and the base. The conjugate of the acid is A minus. The conjugate of the base is Na plus. Na plus, being a conjugate of a strong base, is neutral. And so we need to figure out the pH for this A minus conjugate piece. Cool. A weak species was an acid, so the A minus should be a base. So let's write down a base equation. A minus plus H2O becomes HA plus OH minus. Bases absorb an H plus. This is that kind of a base.
Could you just backtrack for a second and repeat what
Yeah.
you said about the salt and the base? And the conjugates?
Yeah. Since the weak acid is HA and its conjugate is A, right? Acid gives a basic conjugate and base gives an acidic conjugate.
Oh,
So
okay.
yeah, so if this was acidic, then A minus would be basic. And so given that information, I am writing down the basic chemical equation. And in this basic chemical equation, you don't see an OH minus in the base A minus. And so this is the absorbing H plus kind of base. Okay. A minus has a concentration of, let's see, this is 22.5 millimoles. You want to divide that by the total milliliters. Okay, so 50 milliliters of the weak acid was used. And if you go back to the previous question, part B, 11.25 milliliters of the acid was used. That is a total volume of 33.75. So the millis cancel. 22.5 divided by 33.75, 0.6. Okay, so yeah, so this is 0.66. Water don't care. 0 and 0. Minus x plus x plus x. 0.66 minus x, x, and x. And so x squared over 0.66 minus x equals Ka or Kb? It's a base thing, right? OH minus pops up on the other side, so this is KB. This got to be KB. What are we given? We have Ka up here. Let's convert that into KB. 10 to the negative 14 divided by that. Yikes. That is 3.125 times 10 to the negative 11. 3.125 times 10 to the negative 11. That's tiny, small x approximation. Boom. And so x is 0.66 times 3.125 times 10 to the negative 11 square root. And then the last thing that you need to do is take the negative log of that to get POH, since x is about OH, and then do 14 minus. This is probably the hardest question that we've done so far. Okay, any questions?
Shouldn't the total mass be 61.25?
61.25. What did I put? 33. Yes, you are right. 61.25. Thank you. Right, adding up the 50 mils from here and the 11.25 mils from before gives you 61.25. And that was that makes it 0.36. Let me make this 3, 3, 3, and 3. Okay, what is the pH at the 1/2 equivalence point for the acid? For the acid. pH at the half point, remember, is given by just pKa. If it's a weak base, weak acid with strong base, then it's just pH equals pKa. If it was a weak base, you would say POH equals pKb, and then convert this into pH by doing 14 minus. So the half point, you have a very simple relationship. And so it's just the negative log of Ka, which was 3.2 times 10 to the negative 4, given in part A. And you're done.
I'm sorry, I'm a bit confused. Can you just explain that again?
Let me tell you where this comes from. Henderson-Hasselbalch equation goes like this. pH equals pKa plus log concentration of conjugate over acid, right? At the halfway point, the concentration of the conjugate and that of the acid becomes equal. Make sense?
Yes.
So this becomes 1. They cancel and that becomes 1. Log of 1 is 0. And so pH equals pKa.
Okay, I see.
But you don't need to remember this derivation. Just remember that at the halfway point, pH is pKa and POH is pKb. Or you can go about setting up the whole ice table. It will give you the same answer, but why do that?
Wait,
Okay.
so pH is negative log of pKa or pKb?
No, pH is exactly equal to pKa. This was the Ka value given in part A was 3.2 times 10 to the negative 4.
Oh, okay, now I see. And that's how you get pKa from the K.
Yeah,
Okay.
pKa is the negative log of Ka, which is 3.2 times 10 to the negative 4. Excellent. Okay. All right. Moving along. Let me make a quick change. That looks better. You know what? I'm not going to do these sample questions because this is excellent practice for you. Follow everything that we've done upstairs. Oh, you know what? I'll only go over questions that we haven't done. So this we have done. This we have done. This is just Henderson Hasselbalch. Let me give you that hint. This we've done. Okay, let's do question 4. What percentage of C14 half-life is given remains in a sample estimated to be 2.43 times 10 to the 6 years old? This is nuclear decay, first order kinetics. And so it's ln n over n naught equals minus kt, where k is ln 2 divided by t half. We want the percentage of C14 that remains. So we want n, but as a percentage. So n that remains divided by the initial amount of C14 times 100. So if we can solve for n over n naught, all we need to do is multiply by 100. Okay, ln n over n naught equals minus k, which is ln 2 divided by half-life, 5715, and t 2.43 times 10 to the 6. I want n over n naught, so I'm just going to e both sides and then multiply by 100. So n over n naught times 100 will be e to this whole mess times 100. And that's the answer. This is percentage remains. Percentage decayed, however, is given by n0 minus n divided by n0 times 100. But you're not going to use this. You're going to use, let's simplify this. Let's split up the fraction here. So you get 1 minus n over n naught times 100. This is percent decayed. If the question instead said fraction instead of percentage, you would skip the 100. Fraction remains is n over n naught. Done. No 100. Fraction decayed, 1 minus n over n naught. Done. That's it.
I'm
So-
confused about like how you got like whatever you underlined.
Uh-huh.
Can you like explain like what we would do after like we find the E of that parentheses to find the percentage?
Look here. You'd multiply it by 100. So, okay, let me not skip those. Okay, so n over n naught will give you e to the power of this, right? I'm simplifying the exponent to be that number.
Oh, okay, and then whatever you get from that, you just multiply by 100 to get your percentage.
Exactly.
Okay, got it.
Mhm. Five is easy. You should be able to do this. Six is simply asking you to calculate the Ka for this reaction, which is 5 and 6 are basically, no, six is different. Okay, let's just do 6. It's okay. This one is 0.039. pH is given to be okay, let's see. So this is initial. 0 and 0. Change. Equilibrium. Minus x plus x plus x. So you get 0.039 minus x, x, and x. And the pH is given to be 0.039. Which means that the H plus concentration is 10 to the negative 0.039, which is what X is. Cool. The pH allows you to calculate X. And so this number here is also the same. And for this number here, you plug in your X. And then you calculate Ka. Products over reactants. So 10 to the negative 0.039 X times another X, 10 to the negative 0.039 divided by reactant 0.039 minus 10 to the negative 0.039. Okay. Any questions?
What do you do with the 5.07?
That's the pH, right? That was the pH. I'm sorry. pH was given to be 5.07. Yeah. Ugh. That's what goes here. I wrote the pH wrong. I need to eat my breakfast. I haven't eaten breakfast yet. That's why I'm messing up. I'm going to finish this recitation and take a shower, go out, have a nice lox bagel and coffee. All right. Question 7. A 7 mass percent solution of H3PO4 in water has a density of that. Calculate the pH of the solution. Okay. Really? 5 points? You see, H plus occurs in a bunch of different steps, right? Okay, I don't like that. I want one single equation. Let's add up all of these guys together. If we do that, anything that's on the opposite side cancels. So that cancels with that. That cancels with that. And that's it. So what you get is H3PO4 aqueous is an equilibrium with H plus H plus H plus. That's 3 H pluses. We use our usual symbol. Plus PO4 3 minus. What happens when you add up equations to their K values? They multiply. Ka1 times Ka2 times Ka3. That's the K value of this combined equation. Nice. 7% mass. Okay, it's a percent question and it's 7%. So let's start with 100 grams of solution. That means 7 grams is H3PO4, which means, yeah, whatever. Convert that into moles of H3PO4. 3 divided by, what is H3PO4 molar mass? I can't believe this question is 3 points. 90, about 98. 7 divided by 98, which is 0.07. Moles. So all I'm trying to do is trying to get the initial molarity of my H3PO4. So I've got my moles. It's a 100-gram solution, and the density of the solution is that much, which means the volume is density divided by, no, density is mass divided by volume, and so volume is mass divided by density, which is 100 grams of the solution total divided by 1.0353. $96.6 milliliters, which is 0.0966 liters. And so molarity is 0.07 moles from up here divided by 0.0966 liters. Which is 0.72. That's all the information that's given. Minus x plus 3x plus x, 0.72 minus x, 3x, and x. And so x times, no, 3x to the power of 3 times x divided by 0.72 minus x equals this Ka, this product that you've calculated. And when you do it, it should come out to be a very tiny number, which means we can get rid of that. 3 cubed is 27. X cubed times x is x to the 4th power. This is going to be 0.72 Ka. Get rid of the 27 and get rid of the 4, taking the 4th root. And plug in the Ka that you calculate here. Questions? Okay. Let's take a look at question 12 real quick. Delta GF is standard for N2O is given to be 104.2 kilojoules per mole. We want to calculate K. K is given by, no, delta G reaction is given by minus RT ln K. If we want to solve for K, divide both sides by RT, negative delta G reaction over RT equals ln K. Get rid of the ln by eing both sides. And so K equals e to the negative delta G of the reaction divided by RT. This is not delta G of the reaction that is to be determined. Remember from the thermodynamics lecture recording that the delta G of a reaction, much like the case of delta H of reaction and delta S of reaction, is products minus reactants multiplied by coefficients. So it is the formation delta G for the products N2, but there's two of them, so times 2, plus 1 times the formation of oxygen minus 2 times the formation of N2O. Elements always get zeros. They have no formation. Their formation is 0. So this becomes negative 2 times 104.2 kilojoules per mole, which is negative 208.4 kilos, 10 to the 3 joules. So K is e to the negative 208.4 times 10 to the 3. R, this is an energy thing, 8.314. T, temperature in Kelvin, 25 in Kelvin is 298.15. That's your K. Question 11. Use the standard reduction of potentials to calculate the equilibrium constant at 25 degrees Celsius for the reaction. The equilibrium constant is given by E0 cell is minus RT over NF ln Q. No, ln K. This is the equation you have. Have you seen this equation before? This is what connects the equilibrium constant K to potentials. Yeah? Have you seen this?
Yes.
Okay, excellent. So nothing new here. Much like question 12, we're solving for K, multiply both sides by NF, divide both sides by negative RT. That gives you negative E0 cell times NF divided by RT. And E both sides. So E to this mess. First thing to calculate, in question 12, we needed to calculate the delta G for the reaction. Here we need to calculate the E0 cell for the reaction. Remember,
Sorry. For the K equation, is it negative E cell times negative NF?
Negative E cell times negative. No, E cell times NF.
Oh, okay.
Yeah. The negative was technically in the denominator. I just brought it up. It was with RT. I brought it up. Okay, E0 cell is given by the reduction potential of the reduction reaction minus the reduction potential of the oxidation reaction. This is the reduction reaction because electrons are being absorbed, or you can see the charge going down. And so by exclusion, this has to be the oxidation. So that is 0.77 minus oh my God, why would you do this? This is terrible. This formula applies if you are looking at the table. Okay. Here, it's not the table. This is in reduction format. So by table, I mean that both of these reactions should be in the reduction format. The first one is in the reduction format, so it's just 0.77. The oxidation reaction, the E value is not given in the reduction format. If you flip this around, then you get the reduction format, right? Oh, never mind. It is in reduction. Never mind, never mind, never mind. Oh, my bad. This is fine. I marked my oxidation and reduction wrong. If you look closely, this is basically, this question should have had more details in it. Both of these reactions are in reduction format because C electrons are being absorbed in each case. So we can't just by looking at this reaction determine which one's the true reduction and which one's the true oxidation. Okay, let's go back to our equation and compare this with our two reduction reactions. If you look at the first one, Fe3 plus is on the left, Fe2 plus is on the right. If it was truly reduction, this is what would happen. But in the original equation, Fe2 plus is on the left and Fe3 plus is on the right, which means this is actually oxidation. But if you compare the 4H plus and H2O, 4H plus, H2O, that's an exact match. So this is actually reduction. Tricky, tricky. So the E cell here is going to be 1.3 for the reduction minus for the oxidation 0.77. Generally speaking, this should be high minus low. Sometimes they will do it the opposite way just to if they do it the opposite way, they'll say, does the cell below work? And that's where you need to distinguish which one's the oxidation, which one's the reduction, like we did here. And then if you get a negative value for E0 cell, then that means the battery doesn't work. E0 cell should be positive for the cell to work. So this comes out to 0.53. And now let's plug everything in. 0.53. N is the common number of electrons. Okay, 4H plus is a match. So that's a 4. Fe2 plus, Fe2 plus, that has a 4. So times 4 would have given you 4 electrons. So the common number of electrons is indeed 4. So N is 4. Faraday's constant, 96,500. R, 8.314, because it's voltage, energy, same thing, pretty much. Temperature, 25, so 298.15. Any questions? Excellent. You've given a bunch of formation delta HFs, so that means you can calculate delta H reaction using these. You're given a bunch of, this should have been SF. And so you can calculate delta S reaction with these. They're asking you for K equilibrium, which we know is connected to delta G of reaction. But these two are also related to each other via delta G equals delta H minus T delta S. So you're going to use this equation to hop from here to here. And then delta G reaction equals minus RT ln K to hop from here to here. We can do this on your own. Give examples of 3 types of radioactive decay. Alpha, beta, gamma. Choose your favorite atom. Something. I'm going to go with calcium. 40, 20. Let's do an alpha decay, H 4, 2. Figure out the daughter molecule, the daughter nucleus. Let's take that again. Do a beta decay, figure out the X. And let's do 20, 40. Do a gamma decay, 0, 0. And so, of course, this is just going to be 20, 40 again. So here, the bottom number is going to be 18. The top number is going to be 36. Element 18, we'll see in a second. And here, the bottom number needs to be 21, and the top number can be 40. Element. Eighteen should be a noble gas, no? Argon, yep. Element 21 is scandium. Okay. So on an exam, if you're asked the same question, just, choose your favorite nucleus to start with and then figure out what the daughter nucleus should be in each case. Okay, we're almost at the end. I'm going to end by doing question 8. Oof. Calculate the pH of 110 milliliters of 0.34 molar NH3 after the addition of 4.2 grams of NH4NO3 to form a buffer solution. Okay. Henderson Hasselbalch. We have a buffer here. where we have NH3 weak base with its conjugate. So this thing is a salt. Let's break it up. Don't care. NH4 plus is the conjugate. This one is 0.34 molars. Let's calculate the molarity of NH4 plus. So 4.2 divided by the molar mass here will give us the number of moles. Ammonium nitrate is 80 molar mass. 4.2 divided by 80 is 0.0525 moles. And now let's divide that by, and so the idea here is NH4NO3 becomes NH4 plus and NO3 minus. This is 0.0525. Salts completely dissociate in solution to form that and that. Don't care. It's that many moles divided by volume in liters is 0.110. There. 525 divided by 0.110. What? Zero 0.477. Excellent. Henderson-Hasselbalch. This is a weak base conjugate. And so POH equals PKB. What's the PKB? Someone forgot to include PKB. Let me say that it is 10 to the negative 8. No, 8.
I have a question.
Yeah.
So to solve this kind of problem, you set up an ice table
No,
and no.
it's a buffer question. Buffer question, Henderson-Hasselbalch, done.
Okay.
Log concentration of the conjugate 0.477, concentration of the weak base 0.34, and pH is going to be 14 minus POH, and you're done. PKB is 8. I've given you it to be 8. In question B, the concentrations change. If you mess with a buffer, then you need an ice table. So let's see. The NaOH is added to the buffer. NaOH is a strong base. The weak base is not going to react with the strong base because they're both basic. The conjugate, however, is acidic. So the weak base will react with the conjugate. So let's see how that happens. NH4 plus acidic will react with NaOH, strong base, incoming base, to give, this is an acid that will lose an H plus to become NH3. And you will get some Na plus and water. So this gives off an H plus, this gives off OH minus. What's left here is NH3, what's left here is Na plus, and then the H plus and the OH minus combine to form water. This one's tricky. As always, let's do this in millimoles because that is most convenient. NH3 has a 0.34 molarity. Let's multiply that by 110 to get millimoles. 37.4. NaOH, 5 milliliters, and that 5 times 0.087, 0.435. NH, whoops, this 37.4 was for NH3. NH4 plus is 0.477 times 110 again. 52.47. Ne plus, don't really care. Water, don't really care. Anytime a strong species is added, the reaction goes to completion. So the thing present in the lower amount gets fully consumed. So minus x plus x. And so this zeroes out at the end. 52.47 minus 0.435 is 52.04. And here you get 37.4 plus 0.435, 37.84. These are the new millimoles that have been adjusted because of the addition of the NaOH. Okay, this was in millimoles. Let's convert them back into molarities. We had 110 mils from before, and a new volume of 5 mils was added for a combined 115 mils, which is 0.115. So this is 52.04 over 0.115 molarities, and this is 37.84 by 0.115 molarities. So let's do that. Yikes, 52.04 divided by, oh no, we shouldn't divide by liters because we're doing millimoles. Millimoles need to be divided by milliliters to get moles. So the millis cancel. Okay, so that gives me 0.45 molarity. And here I get 37.84 divided by 115.33 molarities. Now we can go back to Henderson-Hasselbalch. POH equals PKB, which I've given you to be 8, plus log of conjugate over base. Conjugate here is 0.45. Base is 0.33. And you're done. So if you're given a buffer, Henderson-Hasselbalch. If you're given a buffer and some acid or base has been added, that is to say the buffer has been messed with, you want to calculate the new molarities of the components of the buffer after the reaction with the strong species has been completed, which is where you do an ice table like this. And then at the end, once you get the new millimoles of the components of your buffer, convert them into molarities, plug them back in to Henderson-Hasselbalch for the new pH. Oh, this is POH, so pH is 14 minus. Any questions?
It's kind of hard for me to follow.
Oh, this part B.
Yeah, I got lost.
Okay. Did you okay. If you go back to A, you had this much molarity of NH3 and this much molarity of NH4 plus, right? And that makes your buffer. When you add NaOH, it will shift that balance, right? Because the NaOH being a strong base will come into your buffer. It will ignore the base, but it will attack the acid. It will react with the acid. So in our buffer, the conjugate was the acid. We react that with the incoming strong base. This is acid-base reaction, which will form some NH3, Na plus, and H2O. So far, so good?
Yeah.
Okay. Initially, we have these many millimoles of NH4 plus, which we determined by multiplying the molarity of NH4 plus by the milliliters of solution. Yeah?
Yeah.
Same thing you do with NaOH. NaOH has this much molarity and this much milliliters. So that gives you 0.435.
Oh, okay. I see now. Okay.
Yeah. And then from there, you just do regular
Figure
stuff.
it out. Okay, cool.
Yep. Awesome. All right, guys, it's time. This is the end of review 1. See you Saturday for review part 2.
Okay, thank you so much.
No problem.
Thank you.
All right.